Good morning, everybody. It's 11:15. Thank you for being here. My name is Dave Pugmire. I'm at Oak Ridge National Lab, and I'm honored to chair this session. We have three fantastic papers. Looking forward to hearing from them. Our first paper is going to be a virtual presentation given by Stefan Zellman, and the title is Hybrid Image Data Parallel Rendering using Island Parallelism.
Hi, and welcome to my talk on hybrid image and data parallel rendering using island parallelism. My name is Stefan Zellman. I am with the University of Cologne. This paper is joint research from people from the University of Cologne, from NVIDIA, people with Mineo University, people from Bilkent University in Turkey, and people from the University of Utah. What we're about to investigate in this talk is scalability on supercomputers and of large clusters, and a default way for people to parallelize their renderer on such a system is sort last parallelism. And in order to reason about the scalability behavior of sort last, let us consider an idealized renderer with an idealized work complexity. We make the assumption, like just for the sake of the argument, that we're dealing with a renderer whose work complexity is logarithmic in the number of input primitives. We will later also see renderers that behave differently, but for the sake of the argument, let us just assume that. We will render like a certain number of pixels, like k pixels, and we will render a certain number of input primitives, triangles, voxels, whatever. And when we add more primitives, the scalability in that is logarithmic. Like a typical example for that is a raycaster that only evaluates primary visibility, and for that uses a BVH. And since we're considering sort last, we're scaling in n. Like we could also scale in k, and then we would talk sort first, but we don't do that. We're considering sort last. Sort last is actually known to exhibit diminishing returns when you add more GPUs to the rendering task. Like when you have like a very large data set that actually saturates the whole memory of your cluster, then you're usually good. But if you have a data set that is somewhat smaller, that maybe saturates like a fraction of the memory of the total system, then devoting more nodes to the rendering task usually shows diminishing returns. Like how does it work with sort last? With sort last, we find some distribution of primitives to cluster nodes. Like here, I'm using like a BVH to organize the data. Like could be anything, could be like a spatial subdivision or a grid or whatever. Then each renderer will render its share in parallel, and then at the end, the renderers will perform image compositing to assemble their intermediate images. This, of course, has like communication overhead. Even this renderer here with this idealized work complexity shows diminishing returns, as opposed to what I'm plotting here in gray would be perfect scalability if we would actually scale linearly in the number of input primitives. The question is really, what is the minimum number of primitives that you want to accommodate per node? And if you go below that, is there any gain from actually going below? And this is, of course, also like a reason for those diminishing returns, because at some point, your subdivisions will become so ridiculously small that it doesn't make any sense to subdivide any further. I'm not going into the details about sort first here, but sort first obviously has the same problem that when we subdivide image space, then we will eventually arrive in a situation where each rank is only responsible for like very few pixels, where it stands to reason makes sense to subdivide any further. To overcome these bad scalability issues, we propose to use what we call islands. The idea with islands is to add data replication as an additional degree of freedom. Suppose the clusters are comprised of 20 nodes, and then we have like half of the ranks of the cluster form an island, and the other half of the cluster form another island. Like we have two islands, and here on this cluster of 20 nodes, each island is assigned 10 nodes or 10 MPI ranks. And on each of the islands, we replicate the whole data set. And then we assign which island is responsible for which share of the K pixels. Yeah. And if we have 2 islands, then we just find an assignment where each island is responsible for half of the pixels. Yeah. This arguably very simple algorithm then goes as follows. We have our assignment of the data to our islands. Each island completely autonomously renders the whole data set for K over num island pixels. And it does so using sort last. Inside each island, we perform sort last parallel rendering. And then in the end, when the islands have finished rendering, we composite the images, like the images generated by each island, but we use sort first. So we don't need a complicated image compositing algorithm, but we trivially composite using sort first. The scalability curve I showed earlier for the simple sort last renderer, that is actually the case where we only have a single island. Yeah. Think of this case as island parallel renderer with only one island. Yeah. Following along, we have like 2 islands, and when we plot the scalability curve for 2 islands, and we say basically the same diminishing returns. But what we also can see is that in absolute terms, we're faster than using one island. Yeah? In absolute terms, each of those data points shows better performance and better scalability than as if we were only using a single island. So obviously, this algorithm is easily extendable. And you can see that by using 4 islands, I again have diminishing return, but in absolute terms, I'm doing better than using 2 islands. Again, this is an idealized renderer with a idealized work complexity that is logarithmic, and real-world renderers will behave differently. But still, for the sake of the argument, this is what we observe. Yeah. So with sort last, we were always interested in those in following along those curves to the right. Yeah, we started from the left and then followed along to the right. But with island parallelism, the curve that is actually of interest is this one here. Yeah, that connects the left-hand data points, because this curve basically shows what we call island scalability. Like whenever we have to make the decision, am I devoting more nodes to the rendering group, like to perform sort last with more nodes? Then I'm going to the right on this curve. And if I instead, I make the decision that when I devote more nodes, I instead create another island, I'm following along this white curve. And we can see that for this idealized workload, that the scalability of this white curve here is much better than the scalability of the sort last curves. While this concept is simple enough, the question that we are interested in is how does this scale and how is the behavior for contemporary workloads? If we apply this to renderers that are typical for today's rendering tasks, how's the scalability of this concept versus scalability of sort last for the same type of renderer? We are generally interested in renderers that can handle both surfaces but also volumes. We're a bit more interested in renderers that are targeted at scientific workloads. We are only going to consider renderers that use some kind of ray tracing. The renderers that we are going to consider are all prototypical, and they are prototypically implemented with MPI. We make use of CUDA, and where applicable, they also make use of optics. So they make use of hardware-accelerated ray tracing where applicable. And our target system that we also later use for the evaluation is the Frontera system. And we are rendering on the RTX partition of the Frontera system, where we have 88 GPUs available. These 88 GPUs are distributed among 22 compute nodes. The GPUs are RTX 5000 cards, and they have 16 gigabyte of memory each. And each compute node is equipped with 4 nodes, and the GPUs are connected using a high bandwidth InfiniBand interconnect. That is, we can directly use DMA among GPUs, even if they are not installed in the same node. I'm now going to quickly introduce the 4 renderers that we are considering and that we implemented prototypically and that were actually implemented by different teams. And the first renderer that we are going to consider is a naive volume ray marcher. And this naive volume ray marcher uses a brick subdivision. Like the volume ray marcher only deals with large structured volumes, and those large structured volumes are organized into same size bricks. We're using subdivisions where one brick is assigned to each MPI rank. And then we have a KD tree that we can use to sort the bricks into visibility. And the data parallel volume ray marcher will perform volume ray marching per each rank, per each brick. And this results in intermediate images. And the ray marching is realized using NVIDIA's CUDA. And it's really like a naive ray marcher where we assign 1 CUDA thread per camera ray. And then in the end, each rank will have intermediate image. And then in the end, we composite those intermediate images using IST. And you can see the communication patterns here, where you can see like we have those blocks here. Those represent the ray marching operation on each rank. Like we have one rank per brick, and we have ranks A, B, C, D, E, F performing ray marching. Then we have a bit of incoherency because we use early ray termination. So some of the ranks will finish earlier than others. And then the ranks will write their image contributions to a local frame buffer. Yeah, this is what happens here. Like this operation here is a local frame buffer write. And after that happens, like there will be a barrier synchronization. So we have to wait until all the local frame buffers are filled. And then at the end, we composite those local frame buffers using radix K. And for that, we use the IST library. Yeah? So this is the overall control flow of our first renderer, and like really like a naive volume ray marcher that only can handle the absorption and emission lighting model for volumes. The second renderer that we are going to concentrate on is way more complex. The second renderer is a production path tracer. And the production path tracer is realized using a ray forwarding layer. So it will, in between bounces, and actually also like for the individual bounces, pass rays around that will traverse the scene objects. This is again realized using MPI. And the subdivision that we use is a BVH. So we're using object subdivision. Each rank knows the whole BVH. It can use the BVH to determine where the data is. And we're also supporting instancing. We're particularly supporting large instance models. The renderer has local frame buffers that it writes image contributions to. And the thing with the path tracer is that image contributions can actually happen on different ranks than the camera arrays were scheduled on. Like we have here the control flow of this renderer. And we have several bounces, like we have 1, 2, 3 bounces. And actually some of the paths that we trace will terminate earlier. Not all of the paths will perform those 3 bounces. And in between those bounces, the rays are forwarded from one node to the other. We have obviously realized this using wavefronts. So we're not sending individual rays, but we instead group the rays and make sure that the communication pattern is efficient. But still, it will in general happen that we schedule a ray on a certain rank, but the ray or the path will actually write an image contribution on another rank. With the ray marcher from before, the only barrier that was relevant was right before compositing, right before the final image was composited. And with our path tracer, we have way more barriers. Like we have to synchronize not only per image, but we have to synchronize per bounce. And not only per bounce, but we also have to synchronize in between bounces. That is, whenever the individual ranks exchange rays in order to compute visibility for the rays that are currently active for their wavefronts. So overall, the communication patterns of this renderer are obviously much more complicated, and so is the workload, which is way more incoherent. The third renderer that we are going to consider is actually quite similar to this renderer, and actually shares code and infrastructure with this renderer, but instead of implementing surface rendering, implements volumetric path tracing. So the overall control flow is actually very similar, but instead of tracing surfaces, this renderer uses woodcock tracking. There's like a probabilistic method to compute free flight distances. And instead of using a BVH and instead of supporting instances, this renderer again supports brick data. Renderer 4 is actually quite different. Renderer 4 is a renderer that only evaluates primary visibility, and it does so by using element marching. This renderer will not march through the data set in equidistant steps, but it will actually march from element to element. It will determine the distance it has to travel to completely span an element with the primary ray. And what's particular about this renderer is it is particularly designed for very large unstructured simulation data, and particularly for simulation data that is allowed to be non-convex. Here, partition A, for instance, this is like the typical output of a finite element simulation as the ones conducted by NASA, for instance. This partition, as it comes out of the simulation, is highly non-convex. And if we evaluate this data set with rays, we generate not a single intermediate image, but we have to generate fragments. And these fragments are arbitrarily interleaved with fragments that are generated on other ranks, and writes those fragments into what we call a deep frame buffer. We have a frame buffer that stores fragments, and it stores those fragments in the order that they are traversed by the rays. And then in the end, the deep frame buffers are composited in the correct order. So we have a much more complex compositing algorithm than we, for instance, have when we implement this with ICE-T. This is our fourth renderer. We evaluated all those four renderers on the TAC Frontera system. The Frontera system is comprised of 88 GPUs, and we use a variety of different data sets, like the aforementioned NASA Mars lander, or the PBRT landscape scene, which is comprised of several million instances, where each of those tiny leaves and vegetation are actually instances. We're also evaluating volumetric path tracing with DVR, but also with isosurfaces. And we're also concentrating on very large giga and terabyte scale structured volumes like the DNS simulation dataset. Here are some of our results. The scalability curves that I show here are similar to the scalability curves that I showed earlier. We can follow those curves horizontally. We can stay on those curves, and that represents scalability in terms of sort last. This bottommost curve here, for instance, is scalability of sort last when adding more nodes to the rendering task, and for that using a single island. Going up in the diagram, the brighter colors signify that we're using more islands. And we can already see, this is renderer 1. This is the structured renderer, which evaluates primary visibility only. We can see what was predicted, that there are diminishing returns. And at the same time, we see that islands actually scale very well. When we follow along, not on those horizontal lines, but we follow along on the contour of the island's curves, then we see that scalability is actually pretty good. When we're, instead of adding extra GPUs inside an island, we instead add more islands. We, of course, also see that at some point the return is also diminishing at some point, which is, of course, to be expected because there's still communication overhead, even if we use islands. But we see that, at least for renderer 1, we scale much better. Without going into too much of the details, what we can also see is that for the path tracers, where the communication overhead is actually pretty high, we have barriers not only per bounce, but inside each bounce, when only following along the sort last curves, we don't only see diminishing returns, but we actually say negative returns. Using sort last rendering only to become faster here doesn't make no sense at all for this kind of renderer. So the only reason to use vanilla sort last with this kind of renderer is to accommodate more data. This is the only reason to use sort last. While at the same time, we see very good scalability from using islands. This slide is basically a summary of the more complex slide from before. which represents an average over the 4 renderers. Like we see that there's diminishing but still a positive return for the 2 renderers, for renderer 1 and for renderer 4. That is the renderers that only evaluate primary visibility, while for the 2 path tracers, we see negative returns for sort last rendering only. While on the other hand, when using islands, that is following along on the contours of those curves, we always see positive returns. The returns still diminish, which is of course to be expected, but the curves actually flatten out much later than the respective sort last curves. With that, I already come to the conclusions of my talk. We investigated sort last parallel rendering versus our island parallel rendering, which is a hybrid of both sort last and sort first. What we propose is to add data replication as an additional degree of freedom to achieve better scalability when rendering on large clusters and on supercomputers. We particularly evaluated this concept in the context of GPU ray tracing renderers. It turned out that islands parallelism actually shows very good scalability, particularly when the workloads are quite incoherent. We conclude that this kind of parallelism is actually pretty underrated. The default modes in typical data parallel renderers, like maybe Visit or ParaView, today is still sort last. Yeah? And we argue that hybrid data and image parallel rendering with this extra degree of freedom of being able to replicate the data should actually be the default mode in any data parallel renderer. And that actually concludes my talk. And now I am happy to take your questions. Hi, and welcome to my talk on hybrid image and data parallel rendering using island parallelism. My name is Stefan Zellmann.
Thank you. Do we have the authors available? We have a minute or two for questions. Yeah, great. If you have a question here, please go to the mic, state your name and affiliation.
Ken Moreland, Oak Ridge National Laboratories. This is a really interesting new take on parallel rendering. Back in the papers that were originally looking at sort last, in the 2000s and earlier, where we had rasterization renderers, which had essentially a linear growth. With the number of primitives. And what you're saying is that now that with raycasting, we have a logarithmic growth. And so it's much better to replicate the data as much as you can. One question I have is that I believe you're looking at the rendering after you've done the BVH. Did you consider the amount of time that it takes to generate the BVH in those use cases where that is applicable?
No, we actually haven't. We focus on very large data sets where building the BVHs, actually, even when we used RTX or optics, would be an offline process, or at least not interactive. So all those numbers that I report don't take data structure construction into account. No, but it would be interesting, of course, to also take into account that the scene is dynamic, for instance.
Right.
Yeah.
I don't know if I can ask one more question. You mentioned that you're using ICE-T as the image compositor under the hood. I know that ICE-T actually does have the ability to declare data replication itself. Did you try to compare it to what's already in ICE-T, or did you just use your own replication?
No, to be honest, I was not even aware that this is possible. I mean, ICE-T generally is like a bit incompatible in that our renderers are they focus on CUDA. Mm-hmm. Well, ICE-T has this OpenGL pipeline, and it's also not possible to share buffers with ICE-T. But to be honest, I wasn't even aware that it's possible with ICE-T to use data replication. And that's good advice for us to also to check out. Yeah.
Okay. Thank you.
All right, we're up on the clock. So thank you. Great talk.
Thank you.
Yeah, I should mention too that we have a Slido active, so ask questions there if you have any, and we'll read them out. So our next talk, will be given by Marvin Peterson and is entitled A Prototype for Pipeline Composable Task-Based Visualization Algorithms.
Yeah, thank you for the kind introduction and welcome to my talk, A Prototype for Pipeline Composable Task-Based Visualization Algorithms. So first of all, let's focus on the pipeline composable visualization algorithms part of the title. So visualization pipelines are used basically every day when we want to create visualizations, and they are a powerful paradigm to create flexible and complex visualizations from basically simple building blocks. There are a lot of tools available for creating those visualization pipelines, for example, ParaView with VTK. And when we are working on larger data or more complex visualization pipelines, then we are taking advantage of parallelism and parallel approaches. The most dominant approach that production software is using is a bulk synchronous parallel approach. Here we distribute our work across processes. These processes then execute. There might also be some communication between those processes, but ultimately they synchronize at a barrier before the next super step. However, this may lead to some inefficiencies where some processes finish earlier than others and the resources allocated are unused. One paradigm, and here we come to the second part of the title, that offers a potential solution for this problem is the task-based parallelism. Here we also subdivide our computation into small independent parts, so-called tasks, that can be represented as nodes in a graph. And we model data flow or dependencies between those tasks as edges in this graph. With this graph and the information of the available resources, an underlying task scheduler can schedule those tasks according to what resources are available and whether the dependencies have been fulfilled. And it is a lot more flexible than the bulk synchronous code approach and allows for many possible execution orders, even for this small example. But how does this transfer to visualization pipelines? In visualization pipelines, let's look at one single module on the left, where we have a task-based implementation of some algorithm. Since it's task-based, we can represent it as a task graph. And since this graph is a directed acyclic graph, you can identify the nodes that have no incoming dependencies and the nodes that have no outgoing dependencies. And we will call them sources and sinks respectively. These sources and sinks are the connection points for other modules in the pipeline so that we can create an even larger task graph for the whole pipeline that you can see here on the right. However, these connection points, of those, we don't want only one, for example, between those modules, because then we would again have created a single point where the computation has to synchronize, and we wanted to allow for interleaving execution of pipeline modules, and thus we're striving for getting a lot more connection points between those modules. So how do we get those multiple connection points? Here we go for a simple data parallel approach where we subdivide the data. So this is common for a lot of parallel approaches. And we subdivide the data in order to distribute it across the compute nodes. But we want to have multiple blocks per compute node, as the blocks directly correspond to the amount of tasks that are the source tasks, for example, of the first algorithm. With this more theoretical foundation out of the way, let's briefly talk a little bit about the implementation and the structure of the framework, which basically consists of 6 components. The first component is the core. The core carries all the information of the algorithm logic and is responsible for scheduling the asynchronous function calls and creating the task graph, the inner task graphs of the modules from the connection points that are given by the sources and the sinks. Those connection points are handed over to the core by the filter, and the filter is also responsible for managing the execution policy and for connecting to other modules of the pipeline via data links. And these data links basically cache the connection points between the filters. Filters and data links constitute a pipeline, and these pipeline objects are managed by a runtime manager. This runtime manager is basically the heart of this framework, as it manages a pipeline, and for the distributed case, as we replicate each pipeline on each node, we also have one runtime manager per node. These runtime managers are special objects, as they are registered in some kind of global address space and are thus able to communicate with each other, and are thus responsible for starting the whole pipeline and also for termination detection. Moreover, they also enable us to do some inter-node communication via messages. Messages are objects that have some information about the source and the destination, but more importantly, they carry information about the connection points of those task graphs, and we can thus create connections between the task graphs of 2 nodes. The framework makes heavy use of the library HPX, which is standard conforming task-based C++ library, and I only want to cover basically 2 small points here about HPX. First is that HPX uses an active global address space. This is also where the runtime manager is registered, and it employs futures for synchronization. Of course, there's a lot more to HPX than futures, but it demonstrates nicely how we create those task graphs. So, for example, we have an asynchronous function called A, and the return of an asynchronous function, the return value of an asynchronous function may come at any time, so we don't know when this asynchronous function will return. So a future is basically a wrapper for this return value, and we are able to wait for this value with this feature. However, and more importantly, we can also use this future as a stub for the return value and hand it, for example, to this asynchronous function B, and now B depends on A, and we have a task graph with A and the data flow going to B. So we evaluated this framework with basically 2 questions in mind. The first is the question after the general competitiveness of the task-based approach. So we want to know whether there is a difference in execution time between both synchronous and task-based implementations. The second question, which directly follows from it, is whether these differences that we might observe stem from the interleaving execution of pipeline modules. In order to answer these questions, we investigated basically 3 setups. First, of course, is the task-based setup. And for the general competitiveness, we include reference runs in ParaView, where we also create similar pipelines. However, these pipelines, of course, are implemented very differently, and thus the comparison is only of general. It's only for general comparison. The third setup that we investigated is a task-based approach with artificial barriers. So here we reintroduce barriers between modules inside the task graph as nodes with dependencies between those modules in order for us to have the same implementation but different different approaches. And we investigated these experiments on 3 prevalent visualization use cases: streamlines, isocontours, and volume rendering, and weak and strong scaling experiments on 1 to 24 compute nodes with roughly 10 gigabytes of data as a vector field. So first, let's jump right into the streamline weak scaling experiments here, and we can see the pipeline structure on the right at the top, and on the left we can see some Gantt charts that show the thread occupation by the tasks, where the different tasks are color-coded. And the top Gantt chart here is the Gantt chart that is coming from the artificially bulk synchronous implementation, and the bottom one is coming from the task-based implementation. However, we don't observe a large difference here from the single run, as most of the work is coming from the data reader and the rest is the particle integration, and they're all neatly scheduled as a block. And we also see this in the efficiency plot here on the right, where we color-coded different block sizes that also are responsible for creating the tasks. Different block sizes in different colors. And the 2 lines of the same color come from the bulk synchronous and the task-based implementations. So again, we see that the block size seems to have a lot more impact overall than the difference between the bulk synchronous and task-based implementations. In more interesting cases, the isosurface extraction and rendering experiment, also here shown in weak scaling experiment, since here in the Gantt charts we can see that on the top it is neatly scheduled in blocks, and on the bottom we see that especially the isosurface extraction here in red interleaves heavily with the vorticity computation of the vector field. And thus we can also see that the rendering is starting way earlier in the task-based implementation than in the bulk synchronous one. However, it does not seem to have a large impact on the overall execution time, since the isocontour extraction and the rendering doesn't constitute much to the overall execution time. In the efficiency plot, we see that now the block size has not as much impact as in the streamline case, and we also were able to include a ParaView reference pipeline, and overall the ParaView reference pipeline shows an efficiency of roughly 2 times better than our implementation. Coming to the volume rendering pipeline that we investigated, here we can see in the Gantt chart that what happens when the scheduler makes a bad decision. So in the top one, we have a volume renderer setup step that is scheduled before the whole execution. However, it postpones the read operation and thus also the vorticity computation. And here between the read operation and vorticity computation, we have basically 5 threads idling. This is something that we do not observe in the purely task-based approach on the bottom, where it is neatly interleaved, and we also see that the read operation finishes even later than in the bulk synchronous case. For strong and weak scaling experiments, we have also a reference ParaView pipeline, and we see in the weak scaling we are generally competitive to ParaView on 12 to 24 nodes, given that we've chosen the correct block size, and in the strong scaling we achieve the same efficiency on 24 nodes, but not before. However, there is some interesting behavior that we can observe with in relation to the difference between bulk synchronous and task-based implementations. As we can see here in the strong scaling experiments on the on 1 to 8 nodes with the largest block size, so the lines here in red, we see that the task-based approach is a little bit better, is a little bit faster, and we believe that this is due to the low number of blocks that the task scheduler is able to schedule. And of course, without barriers, the task scheduler can also profit from the next steps in the pipeline, in contrast to the bulk synchronous approach. So we see a little bit better behavior here. And we can also see the same effect in the green line. So the second largest block size, also in the strong scaling experiments, from 12 to 24 nodes, where the bulk synchronous becomes worse, where the task parallel approach stays roughly the same. And here in the strong scaling experiments, we of course have a fixed number of block size, a fixed number of blocks, and thus when we increase the number of compute nodes, then we decrease the number of blocks per node, and thus the task scheduler is then less flexible. With these results, I want to wrap up my talk. So we presented a framework for composing task-based visualization algorithms into pipelines, and we showed that there could be a potential benefit of interleaving execution. However, most of the investigated pipeline modules suit really well to the bulk synchronous parallel model. But to give a positive outlook, we may take advantage of the task-based paradigm in pipelines and algorithms where we produce load imbalance, where they produce load imbalance not only at the end of pipelines, but also in the middle and the start, and where the load imbalance producing algorithms and the algorithms following them are computationally intensive enough to overall affect the complete execution time. Thank you.
Okay, thank you. Great talk. We have some time for questions.
Hi, my name is Chi. I'm from UC Davis and Organization Lab. I have a question for your work. Have you considered? When we are working with task-based programming model, one issue is we have to take care of data movement between ranks, between tasks. Does your model handle this completely, or is still allow you? For example, if you have two tasks running in parallel, and then they need to communicate internally within the task, they want to share data, they want to talk to each other. Does your runtime handles this completely? If so, wouldn't that be very complicated to do in general?
Okay, so the tasks themselves are independent of each other. So one task does not communicate with another task if it has no dependency to it. So this is one thing. But however, the task scheduler does, for example, work stealing on one compute node. And it can somehow load balance on one compute node, and for multiple, so for communication across localities, there one also would use a dependency inside this task graph. So all communication is basically also represented in this task graph, and so we do not have to directly care about that.
Okay, thank you.
Thank you for your question.
Any other questions? I have a quick one. Have you considered, in the context of time varying data where the complexity is going to vary over time, have you looked at how your system scales compared to the bulk synchronous You have any thoughts on that?
So we haven't looked at time varying data yet. However, so I can imagine having multiple pipeline executions after another, and then of course these pipelines, if executed by the same runtime system and by the same scheduler, then one would also profit from interleaving both those pipeline executions. So, for example, if we have the first time step, and then and it is not that computational intensive, one could start the second one earlier or parts of the second one earlier.
Yeah, and I meant too is, as different parts of the data, the complexity changes and grows within, so you've got, the complexity spatially is going to vary over time too. Does that make sense?
So you mean like adaptive mesh refinement data?
Yes, something like that.
Yes. So changing the amount of tasks that you can schedule is not really a problem. So one could, so even in this framework, one could easily change the amount of tasks and even the block size during the execution. One would have to add a step that basically splits up the blocks or merge blocks depending on the overall workload that appears.
All right. No further questions. Let's thank the other. Fantastic talk. Thank you. Okay, our final paper for this morning will be presented. This will be a remote presentation by Aniketh Venkat. And the title of the presentation is High Quality Progressive Alignment of Large 3D Microscopy Data.
Hi, I'm going to present our paper, High Quality Progressive Alignment of Large 3D Microscopy Data. Recent advances in microscopy have enabled researchers to acquire images at high resolution and magnification. A consequence of the high magnification is that the samples are often too large to fit into the field of view of a microscope. Therefore, to image an entire specimen, computer-controlled micropositioning stages are used to acquire images as overlapping 3D tiles arranged on a two-dimensional grid. A range of movements occur during an acquisition that often results in misalignments, and precise alignment of many overlapping 3D tiles is therefore required to reconstruct a 3D image. Our new progressive approach to align large 3D microscopy data can align a 616 gigabyte image in 4.97 minutes. It is 2.6 times faster than the state of the art, and it requires 6.5 times smaller memory footprint. It is typical for microscopy acquisitions to create several terabytes of data in a single session. For example, a 7 by 11 tile dataset imaged at 2K cube resolution with 16-bit precision creates 616 gigabytes of data. Due to their sheer size, aligning many overlapping gigabyte-sized 3D tiles in parallel and at full resolution is both memory-intensive and I/O bound. Prior solutions often circumvent the problem by computing alignments using downsampled images. Very few techniques have explored coarse-to-fine alignment, and majority of the approaches trade quality for performance. In contrast, our approach is truly progressive and adaptive. It utilizes all the resolution levels in the data to systematically find regions where fetching higher resolution samples matters the most for alignment. Our approach is based on a key observation that if we subdivide the overlap region into subblocks and align corresponding subblock pairs in a coarse-to-fine manner, then the majority of the subblocks can be safely pruned after examining their inexpensive coarse-scale alignments. In order to efficiently identify the subblocks to prune during a coarse-to-fine alignment, we devised a new progressive refinement and pruning loop that starts at the coarsest resolution level 0 and runs until the full resolution L. At full resolution, only a few subblocks remain after coarse-to-fine pruning, and aligning these subblocks is sufficient to obtain an accurate result. Here we show the overlap region with subblocks shown as bounding boxes. Here we see a progressive approach in action. We only show the overlap region of two overlapping tiles, rendered using contrasting color palettes to highlight the initial misalignment. At the coarsest resolution level, we align all subblock pairs, and with each refinement in resolution, we identify and realign only the subblocks that are likely to contribute to the final result, discarding the remaining subblocks. At full resolution, only a few subblocks remain, and aligning these subblocks is sufficient to obtain an accurate result. Here we show the overlap region before and after alignment. Notice aligning only the few remaining subblocks is sufficient to obtain a high quality alignment. Our progressive refinement loop consists of 4 major steps. In the first step, we fetch subblock data. To fetch subblock data at multiple resolution levels efficiently, we utilize the IDX multi-resolution file format. IDX scheme stores the grid of samples G as a series of nested subgrids, with each subgrid containing half the number of samples as its parents in one of the access directions. We denote each subgrid as a resolution level, with G0 being the coarsest resolution and GL being the finest. On disk, resolution levels are stored separately as blocks, and within each level, individual data samples are sorted using Morton codes prior to blocking, so that conceptually, each sample is a leaf of a KD tree, and the root represents the entire domain. Given an extent E, which is the subblock bounding box in our case, and a resolution level, IDX quickly traverses the KD tree in logarithmic time, identifying the blocks that overlap E at resolutions no finer than the requested level. It then prepares and outputs a buffer with the relevant samples. Because the resolution levels are nested, suppose we query the same extent E at a final resolution level later, IDX only fetches the samples corresponding to the final level blocks from disk, and it avoids refetching the entire block, which is an expensive operation. In the second step, we compute pairwise subblock alignment by maximizing the normalized cross correlation between the subblocks. We assign a 3D translation in the reliability scope for each subblock pair. At coarse resolution levels, we compute NCC in 3D, and at finer resolution levels, where 3D NCC computation is expensive, we replace it with a faster 2D approximation based on maximum intensity projection at 2D NCC. We call this as the hybrid mode. We allow the user to choose the resolution level at which to switch from 2D to 3D to 2D computation. In the third step, we partition the subblock translation space into clusters and subclusters and assign a probability value for each cluster and a subcluster. We use dbScan to perform the clustering. There are two advantages of using dbScan. First, it does not make any assumptions on the number of clusters a priori. And second, it groups nearby objects into a single cluster. This is important because we compute alignment in a coarse-refined manner. Subblock translations can be slightly off from one another. In stage 1, we group subblocks with epsilon distance equal to 1 into unique clusters. Stage 1 is usually useful in identifying and eliminating outliers, shown as pink bounding boxes here. In stage 2, within each cluster, we group subblocks with identical transformations into unique subclusters, shown as unique colored bounding boxes here, and we assign a probability value for each cluster and a subcluster based on the relative sizes. In the final step, using the computed probabilities, we identify the subblocks to refine at the next resolution level using weighted random sampling. We first select the subblocks to refine without replacement one at a time by first selecting a cluster using the cluster probabilities as weights. Next, within the chosen cluster, we select a subcluster using the subcluster probabilities as weights. And finally, within the chosen subcluster, we pick the most reliable subblock to define first at the next resolution level. Once the required number of subblocks to define at the next resolution level are found, we increase the resolution and repeat the loop until full resolution. At full resolution, to determine the final transformation, we align the remaining subblocks and group subblocks with identical transformation into unique clusters. We then discard the clusters with average reliability score less than or equal to 20%. And from the remaining clusters, we identify a candidate subblock as the representative for the final transformation, as the subblock which has the highest reliability score in the largest cluster. From the remaining clusters, we pick additional candidates as subblocks whose translation is within 5 voxels from the initial chosen candidate. Finally, we assign a final translation for the pair of tiles using the subblock whose translation is closest to the centroid of the candidate subblocks. Here we show an example before and after alignment. Notice before alignment, the overlap region has repeating patterns, and after aligning only the few remaining subblocks, we see a more coherent looking overlap region. The success of our coarse-to-fine alignment algorithm is contingent on how we choose the minimum resolution to start pruning subblocks. At very coarse resolution levels, alignment computations can be unreliable, and any mistakes made at coarse scales can make it impossible for fine scale alignments to succeed. In order to reliably choose the resolution level to start pruning, we devise the following steps. First, for each successive resolution levels, starting from the coarsest resolution level, we align all the subblock pairs, and we group subblocks into informative and non-informative subblocks by clustering their translations. Subblocks that belong to a cluster are encoded as informative subblocks, and subblocks that do not belong to any cluster are encoded as the non-informative subblocks. We then find the percentage of subblocks that change from informative to non-informative and vice versa, and find the resolution level at which the percentage change is below a user-defined threshold. Here we see an example. Pink bounding boxes correspond to non-informative subblocks, and blue bounding boxes correspond to the informative subblocks. We start from the coarsest resolution level 0. Between resolution 0 and 1, the number of sublocks that change from informative to non-informative and vice versa is above the user threshold. Between 1 and 2, the percentage is still high. But notice between 2 and 3, number of sublocks that were informative majority of them remains informative, and the majority of the non-informative subblocks continue to be non-informative subblocks at resolution 3. We therefore call resolution 3 as the prune start resolution level, and we start discarding subblocks from resolution 4 onwards. To test whether our algorithm correctly discards the subblock at each refinement level, we aligned 117 tile pairs using our progressive approach, and we measured the L2 error between the subblock's full resolution transformation and the ground truth computed using exhaustive search. Here, each point corresponds to a subblock, and the color encodes the resolution at which the subblock was discarded. The proximity of the points to the y-axis signifies the importance of a subblock. Points closer to the subblock, closer to the y-axis, provides translation closer to the ground truth. Notice at fine resolution levels, the sublocks that were refined are the informative sublocks. The sublocks that were eliminated early at coarser resolution levels are the sublocks that do not contribute to the final result. Here we compare our alignment of various modes of our algorithm with the state of the art, big stitcher and thin stitcher. Our fastest mode refines 1% of the subblocks at full resolution, and it uses hybrid mode. It is 2.6 times faster than big stitcher, and it requires 6.5 times smaller memory footprint. Our fastest mode also produces a higher quality result. Here, we provide an example. Notice the RMSE of our approach is lower than that of big stitcher. Defining a higher percentage of subblocks at full resolution produces a higher quality result at the cost of runtime. Refining 20% of the subblocks using hybrid mode produces a significantly higher quality result compared to big stitcher. However, it runs at a comparable runtime with big stitcher. Here we show an example by refining 20% of the subblocks using our algorithm and with big stitcher. Notice our algorithm produces significantly lower RMSE compared to big stitcher. There are several issues in the big stitcher aligned image, and the reason for this is Rig Stitcher uses 16x downsample images and phase correlation to compute the alignment. In contrast, we efficiently identify the regions where fetching higher resolution samples matters the most for alignment, and find the final transformation using a few full resolution blocks, thereby guaranteeing a higher quality solution. Finally, the difference between our full 3D solution and the hybrid mode is small in terms of the alignment quality. However, the speedup is significant. Our hybrid mode runs 6.8 times faster than the full 3D solution. For applications where accuracy is important, the users can use 3D mode to compute alignments at all resolution levels. And for applications where speed is important, users can choose hybrid mode and optionally skip resolution levels during the refinement to further improve the speed. We refer to the paper for a more detailed analysis on the various modes of operations and parameter tuning. In conclusion, we introduced a novel, fast, progressive approach to align large 3D microscopy data. Our approach fetches higher resolution samples where it matters most, and it discards majority of the data at coarser resolution levels using inexpensive coarse scale alignments. We provide flexible choice of quality versus speed with various modes of operations, and our approach is 2.6 times faster than the state-of-the-art Rig Stitcher. It requires 6.5 times smaller memory footprint, and it produces a higher quality result. In the future, we plan to extend our algorithm by including affine and nonlinear transformations, and to adapt to various other imaging modes, such as electron microscopy and digital pathology images, that come with their own challenges. I would like to thank you for your attention, and I'll be happy to take any questions.
Any questions? And if you have any questions on Slido, please make sure you. Oh, we have a question here from Haoyo Lee. Since the accuracy depends on the chosen coarsest resolution, how do you choose the hyperparameter?
So the hyperparameter is chosen based on, so at each coarse resolution level, starting from the coarsest resolution, we align all the subblock pairs, grouping the subblocks into informative and non-informative subblocks. And we find the percentage of subblocks that change between resolution levels. When the percentage is below a user-defined threshold, usually it is 10%, we start pruning subblocks. So yeah, to answer your question, the hyperparameter is chosen based on a user-defined threshold. And in the paper, we've shown how different thresholds affect the alignment quality. Choosing a higher threshold usually performs slower, but provides a higher quality result.
Thank you. Any other questions? I had a quick one. So on one of your slides, you mentioned that the success of the process relies on the appropriate coarse scale selection.
Yes.
Do you know if you didn't succeed? I mean, basically, do you realize that you get to the end, oh, this didn't succeed, so I need to go back and adjust the coarse scale? Is there a mechanism to do that?
Yeah, so the process is adaptive. For each tile pair, we don't use a fixed coarsest resolution where we start pruning subblocks. Based on the data, some tile pairs can start pruning at very coarse resolution levels if the signal to noise ratio is very high. And for some for some tile pairs where the signal quality is low, we go until a resolution 5, which is defined as the maximum resolution level, above which we start pruning subblocks, even though we don't succeed in finding enough signal. So the success of the algorithm doesn't depend on the doesn't really depend on which resolution we start from. It only, the performance of the algorithm is affected by which resolution we start pruning the blocks.
Okay, great, thanks. Any others? Okay, let's thank our speaker for a very interesting talk. Thank you. Let's see, that wraps up the morning session. We're a little bit early, so get a jump on lunch. Let's thank again the speakers. Three fantastic papers, and we'll see you all. And we will reconvene, I think, at 2 o'clock, if I remember correctly, right? It's 2 o'clock after lunch. So thank you. Enjoy the rest of your day.